Assalamu alaikum. Dear students, I welcome you to the fifth lecture of probability and stochastic processes. In the previous four lectures, we have covered the basic mathematical tools that we need to analyze random phenomena, and we applied these tools to some simple problems. Particularly, we studied sets and vectors, cardinality of sets, Cartesian product of the sets, and cardinality of Cartesian product of the set. We also discussed relations and functions, and then we applied all these mathematical tools to analyze random phenomena by putting all outcomes of a random experiment in a set and calling it a sample space. Then we formed subsets of this sample space and put them together in a collection called sigma field. And from this sigma field, we assigned numbers to events such that the numbers lie between 0 and 1. So probability is a function which assigns numbers to events where events are subsets of sample space. Since probability is all about assigning numbers to events, it's possible for us to combine events to make new events and assign probabilities to them without going back to all the outcomes in the combined event. That is, if you know probability of one event, say A, and probability of another event, say B, then you can combine the two events A and B and form a new event C and find the probability of C from the probabilities of A and B. Actually, we have already talked about combining events to make new events. If you remember, when we were talking about axioms of probability, one of the axioms says that if you have two disjoint events, then probability of their union is equal to sum of the probabilities of the two events that are used in the union. Actually, we talked more. We said even if the two events are not disjoint, you can make their union, and then the probability of the union of the two possibly overlapping events is equal to sum of the two probabilities minus the probability of the region which is intersection of the two sets. Let's talk more about this intersection of two sets. This is an event. We need it sometime, and this has interesting applications. If we have two events A and B, then there is something called joint probability. The joint probability is the probability of these two events A and B happening together. What do you mean by together? You see, when you perform a random experiment, you observe an outcome, and it is possible that this outcome belongs to two sets simultaneously. Then, whenever you observe that outcome, you say both of the events have occurred. For example, you roll a dice and you observe its output. And the two events that we have defined are A, that the outcome is an even number, and B, the outcome is less than 4. It is either 1, 2, or 3. So suppose you roll a dice and observe 2. This outcome 2 belongs to event of even numbers, and it also belongs to that event of outcome being less than 4. So whenever you observe outcome 2, both of these events have occurred jointly. For other outcomes, it's possible that one of the two events occurs or none of the events occur. For example, you roll a dice and you get 1. Then this outcome does not belong to the set of even numbers. So that event has not occurred. But the other event, where the outcome should be less than 4, has occurred. And another example, if you roll a dice and get 5, then neither of the two events have occurred. The 5 is neither an even number nor it is less than 4. So depending upon the outcome and the two events under consideration and their relationship, the relationship between two events, it's possible for the two events to occur jointly sometimes and sometimes not jointly. So this new event where the two given events A and B occur jointly is called joint probabilities. So probability of that event where both of them have occurred is called a joint probability. And if you draw a Venn diagram, you can see that in Venn diagram, this event is represented by the intersection of the two events. So if the outcome belongs to the intersection of the two events, then whenever an outcome lands there, both events have occurred. Depending upon how the two events are interacting with each other, we can find the joint probability. For example, in the case of roll of a dice, if the two events are A, that the outcome is an odd number, and B, that the outcome is an even number, then these two events are disjoint. There is no overlap. If the outcome belongs to odd numbers, it cannot obviously belong to even numbers, and if it belongs to even numbers, then it cannot belong to odd numbers. So whatever the outcome of roll of a dice, these two events cannot occur jointly. The probability of these two events occurring jointly is 0, which is obvious because the events are disjoint and there is no intersection. The intersection is empty, and according to the postulates, axioms of probability, the probability of an empty set is 0. So if the two events are disjoint, they cannot occur jointly. And if one event happens to be subset of the other, then the outcome is very interesting. Suppose there is an event E and there is an event F, and event E is subset of event F. So whenever an outcome lands in E and E is subset of F, it has also landed inside F. So whenever E occurs, F automatically occurs, and their intersection is set E. So in this case, the probability of joint event, the joint probability of E and F, is simply equal to probability of E. In general, two sets will have some overlapping area, and then the joint probability will be the probability of that intersection area, the probability of all the outcomes in that area, sum of the probabilities of all the outcomes in the intersection area. There is another way we can combine events to form new events, and that has to deal with the way probability theory works. As you know, probability is all about lack of information or partial information or complete information. So if there is a random phenomena with unpredictable events, it's possible that you have no information or you may have some information. So if you receive some information, then this event of receiving some additional information can be combined with other events where you have no information to form new events, and probability of these new events has very interesting applications. This phenomena of providing additional information is called conditional probability. So if there is an event A and you know its probability, and then you are told that another event has occurred, the random experiment was performed and another event has occurred, the output belongs to that event. With this additional information, can you find new probability of A? That is conditional probability. Let's take an interesting example. Suppose your friend rolls a dice on the table but hides the dice from you with his hand. So the dice has been rolled, it has come to rest, but behind the hand of your friend. You don't know what is the top surface, how many dots are there on the top surface, but your friend knows. To you, the outcome is completely random. You cannot have preference of one outcome over the other. So to you, all 6 possible outcomes are equally likely with the probability of 1 over 6. But your friend knows what is the outcome of this roll. He knows how many dots are on the top surface. He looks at that and tells you that the outcome was not equal to 6. He does not tell you the exact answer. If he tells you exact answer, then it's not a probabilistic problem anymore, it's a deterministic problem. But he gives you just little bit of information that in the previous role, the outcome is not equal to 6. This information is certainly useful in a sense that now you know that the outcome belongs to the remaining set of 1, 2, 3, 4, and 5. But still, the problem is random to you. You cannot have preference for one outcome over the remaining 4. So with this additional information of outcome not being equal to 6, the nature of the unknown has been changed. Previously, the unknown was the whole sample space. The outcome could have been any one of the outcomes in the whole sample space. But with this additional information, the sample space has been reduced. New restricted sample space contains just 5 outcomes, 1, 2, 3, 4, and 5. And it is logical to assume that the outcome is equally likely. At least to you, it is equally likely to occur either as 1, 2, 3, 4, or 5. So without any information, probability of outcome being 1 is equal to 1 over 6. And with this additional information that the outcome is not equal to 6, the conditional probability of 1 has increased to 1 over 5. So with this additional information, it is 1 over 5. There are other kind of information that you can get which change the probability of an event. For example, if we continue with the example of this roll of dice, and your friend rolls a dice and tells you that the outcome is an odd number. In that case, the probability of the outcome being 1 is 1 over 3. Why? Because this new information tells that the outcome can be either 1, 3, or 5. And the new restricted sample space has just 3 outcomes, and to you, all should be equally likely. So in this case, the probability of 1, given this information that the outcome is an odd number, is 1 over 3. And if the information given is that the outcome is an even number, then probability of the outcome being 1 is 0. So without any information, probability of 1 is 1 over 6. And with the different kind of informations, partial informations, the nature of the unknown gets changed, and the conditional probability with this new information also gets changed. Sometimes it increases, as was the case when probability of 1 being 1 over 6 in the complete lack of knowledge case moved to 1 over 3 when you were told that the outcome is odd number. And it can reduce also when probability of 1 being 1 over 6 goes down to 0 if the additional information is that the outcome of the experiment was an even number. So how do you mathematically combine these events which provide you additional information? So if you have an event A and its unconditional probability with complete lack of knowledge is given, and then you are told that the experiment was performed and the outcome belonged to set B, then you know the restricted new sample space where the outcome could be. It cannot be outside B. So this new restricted sample space is the B set, which is given to you that the last performance of the experiment resulted in an outcome which landed in B. So this set B is your new restricted sample space. Now, how this B interacts with A determines what will be the conditional probability. This will be clear if you look at the next slide, in which we have a Venn diagram with events A, B, and C drawn as closed figures. In this Venn diagram, the outer rectangle, which represents the universal set, has been labeled S. Now S is our sample space, and our sample space is the largest set that is useful superset of all the events that we are going to consider. So let's look at this Venn diagram and explore how different sets interact with each other to give meaning to conditional probability. If you look into this Venn diagram, the outer rectangle, the sample space is S, and all other closed figures are subsets or events. So if experiment is performed and you are told additionally that the outcome belongs to set B, the event B has occurred, then this new information changes the probabilities of different events. First, look at C. If you are given additional information that when you perform the experiment, it landed in B, then it could not have landed inside C because C and B are disjoint. So probability of C, given the additional information that B did occur, is equal to 0. The probability of C itself, unconditional, could be non-zero, but when you give this additional information that B did occur and B is disjoint with C, then probability of C given B is equal to 0. Let's look at A. What is probability of A given B? First, look at unconditional probability of A. It is the sum of probabilities of all outcomes that belong to A. But if you give additional information that set B did occur, then new restricted sample space is just the interior of set B. And then probability of A given the set B increases because the region of uncertainty got reduced from S to B. Now event A is more likely to occur because of reduced region of uncertainty. So probability of A given B will increase, whereas probability of C given B decreased and became 0. Lastly, let's look at event D. It is not a subset of B. It has some overlap with B. So what will be the probability of D given that B has occurred? It will be the sum of probabilities of all the outcomes which are in the intersection of D and B, the joint probability of B and D. But how do you find it? Once again, you look at the reduced uncertainty region B, and then you look at the intersection of B and D, and you get your probability by finding the outcomes which land in this intersection region. Let's look at a special case. Probability of B given that B has occurred. It may sound silly, but it is a useful thing to start with. B is an event, and if you talk about unconditional probability of B, it will be non-zero. But if the random experiment is performed and you are told that event B has occurred, then you are asked, with this additional information, what do you think is the probability of B? Of course, it is 1. Once you are told that event B has occurred, it's a certain event, it has occurred, so probability of B given that B has occurred is 1. And we have already checked that if the events are disjoint, if B is disjoint with C, then probability of C given that B has occurred eliminates or makes it impossible for C to occur. If B has occurred, C cannot occur, and the probability is 0. So all these things get combined together, and we see that the conditional probability of A given B depends on two things. What is B? What's the probability of B? What is the reduced region of uncertainty? And what is the area that is overlapping between A and B? If you are trying to find probability of A given B, you have to know what is region B and what is the intersection between A and B. And the formula happens to be, as it is given in this slide, is that probability of A given B is equal to division of joint probability of A and B and probability of B. So you take the intersection region and find its unconditional probability and scale it up by dividing it with the probability of reduced uncertainty region. Usually the additional information about the outcome belonging to a certain event changes the condition probabilities of other events compared to their probabilities without this additional information. So when you provide additional information, the conditional probability becomes more or less than the unconditional probability. But it's quite possible that even with additional information, the probability does not change. The conditional probability and unconditional absolute probability remain the same. In that case, we say that the two events are independent. If there is an event A and there is an event B, and probability of A, the absolute probability, unconditional probability is same as probability of A given B, then this additional information about B having happened does not alter the probability of A. The unconditional and conditional probability of A conditioned on B remains same, and these two events are independent. If you look at this Venn diagram again, you will see that conditional probability of C given B is 0. These two are disjoint. Most students confuse independence of two events with them being disjoint. When two events are disjoint, then the conditional probability of one conditioned on other is 0, because once you are told that the outcome belongs to one set, the probability of other set is 0. But the unconditional probability of the other set would be non-zero in general. So to have independence, the sets must overlap. Not only that, but the ratio of the joint probability divided by probability of the set upon which you are conditioning should be same as the absolute probability of the event. In this Venn diagram, the ratio of the intersection region between D and B, we are taking D and B because they have some overlap and they are good candidates for checking independence. And in this Venn diagram, if you assume that all these figures have probabilities proportional to the enclosed area, even though this supposition is against the spirit of Venn diagram, but for the sake of argument, we'll go along and say that in this Venn diagram, the enclosed area represents the probability of an event. So the enclosed area of the rectangle S is 1 because the probability of whole sample space is 1. Similarly, probability of A is smaller than B because A is subset of B, and the probability is equal to the area. So unconditional probability of D is equal to its enclosed area, which will be less than 1. And the conditional probability of D given B will be ratio of the area of the intersecting region and the whole area of B. If this ratio also happens to be a number smaller than 1 and equal to the area of D, then events D and B are said to be independent. If you look carefully at this Venn diagram and assume that even D is independent of B, that is, probability of D given B and its absolute probability is same, then event B is independent of D. That is, probability of B given D is same as probability of B without additional information. So if two events are independent, they are independent in both ways. Information about one does not change the probability of the other, and information about the other does not change the probability of the first one. Independence of events can manifest itself in different ways. If the experiment is a simple type which gives an outcome, then this outcome can belong to many events. And some of these events may be independent of other if they satisfy the criteria we just discussed. But if the experiment is a multi-part experiment where the outcome is a vector-valued observation, and these vector-valued observation pairs or triplets or quadruplets of observations are grouped together to form events, then a new way of independence can be investigated. Suppose you have a multi-part experiment and you have events, and one event is such that it only depends on the first part of the experiment, and the second event is such that it only depends on the second part of the compound experiment. Then if these two events are independent, we can say that the two parts of the experiment are also independent. This will be clear if we look at the next example. In this example, we'll perform a multi-part experiment. A multi-part experiment can be performed as a joint experiment, or it can be performed as a cascade of two experiments. And in this experiment, we'll continue with an example from the previous lecture where we had a sack, and in that sack we had balls of two colors, green and red. Now let's take two sacks and reduce the number of balls in those sacks. So we have one sack on our right, one sack on our left, and both of these sacks have 3 green and 2 red balls. So this is how a joint experiment could be performed. You shake the two sacks, put your hands in the two sacks and take out 2 balls simultaneously and note down the colors of the balls and combine these two observations as a pair of observation. So you can have first observation the color of the ball in the left hand and the second observation at the color of the ball in the right hand. Or you can throw away one sack, take one sack, put your hand, take out a ball, note its color and make that your first observation. Then you can put the ball back in the sack, shake it and take out the second ball and note its color, and that will be the second part of the observation. And here you have a choice. You can either put the ball back after the first part of the experiment, or you can discard the ball and perform the second part of the experiment without that ball which came in the first part of experiment. These two types of cascaded experiments are called with replacement and without replacement. If you perform the first part of the experiment, make an observation and restore the nature of your experimental setup by putting the ball back, you are performing the second part of the experiment with replacement. And if you throw away the ball, then you are doing it without replacement. So you can go both ways. But this kind of multi-part experiment can have pairs of observation, and these pairs of observations can be combined to form events, and these events can be studied for their independence with each other. Let's look at the sample space of this experiment. The first part of the experiment will have 5 possible outcomes. Let's call these outcomes green 1, green 2, green 3, red 1 and red 2. These are the 5 balls in the sack. And the second part of the experiment also has green 1, green 2, green 3 and red 1, red 2. And when you combine the two experiments, it's a 2-part experiment, then the cardinality of the whole space of pairs of observation will have 25 entries, and that can be arranged in a grid. This grid can be seen in the slide where we have 25 entries, pairs of observation, and we can form different events on this sample space. Let's look at the first interesting event. The first interesting event is that the first ball was green. So if you look at this sample space, you can see that there are 15 entries where the first entry is G. It can be G1 or G2 or G3, but there are 15 entries where the first entry is G. So what is the probability of this event that the first ball observed was green. You see, this experiment, this event does not depend on the outcome of the second part of the experiment. This event is just talking about the first part of experiment, that is, we got a green ball when we performed the first part of the experiment. But we are looking at whole two-dimensional sample space. Looking at the slide, you see there are 15 such entries where first entry is G, and if all outcomes are equally likely with the probability of 1/25, then probability of this event that first ball was green comes out to be 15/25 or 3/5. Similarly, if the event is that first ball is red, it will have a probability of 2/5 because there are 10 entries in the two-dimensional sample space where the first entry is R. It can be R1 or R2. So these events have probability of 2/5 and 3/5. And if you look at just the first part of the experiment and see that the sample space of the first part of the experiment is just 5 entries, G1, G2, G3, R1 and R2. And if they are equally likely, the probability of getting green ball is 3/5 and getting red ball is 2/5. Let's look at some other interesting events. If we define our next event to be that the second ball is red, and we also assume that all outcomes are equally likely, and that is only possible when you perform this experiment as a joint experiment with 2 sacks of balls or as a cascaded experiment with replacement, then all outcomes are possible. Particularly this type of outcome where the first ball observed was G1 put back and second ball was also G1. This kind of pair of observation is not possible if you had thrown away G1. So assuming that the experiment was either a joint experiment or cascaded experiment with replacement and all 25 entries are equally likely, then the event probability that second ball is red has probability of 2/5 and second ball being green has a probability of 3/5, and you can confirm that by counting the number of places out of total 25 places where this event has an outcome belonging to it. Now suppose I give you additional information, and this additional information is in the form of an event which is written on this slide as C, and event C is that experiment was performed without replacement. You are assuming that everything is equally likely with a probability of 1/25, and suddenly you are told, no, this experiment was performed without replacement. The ball was drawn in the first part of the experiment and it was thrown away before the second part of the experiment was performed. How does this additional information that the experiment was performed without replacement change the nature of the unknown? Now, only possible outcomes are the top diagonal and bottom diagonal entries. The main diagonal, where the entries like G1, G1, G2, G2, G3, G3, R1, R1, and R2, R2 have been eliminated. They are not part of this set C. Set C tells that the top diagonal, upper triangular, and the lower triangular events are the only possible events, and they are 20 of them. So if you have defined this C, the new piece of information, as an event, then the probability of C is 20/25, because out of the total 25 entries, now only 20 entries are possible and 5 entries have been eliminated. They have been impossible to perform because the experiment was performed using this without replacement technique where the ball was thrown away. So how does this change the probabilities of other two events A and B, where A is that the second ball was green, and B is that second ball which was drawn is red. If you apply the formula of conditional probability and find the intersection region of the two events, that is the second ball being green combined with that the experiment was performed without replacement. You can count the number of places, find the probability of intersection region. You have already found the probability of C, which is 4 over 5, 20 over 25 over 4 over 5. You find out that these probabilities are again the same. If you look in this slide, you see that probability of A given C is the ratio of probability A into C, and the intersection region A and C contains 8 entries. Each of these entries has a probability 1 over 25. So probability of A and C is 8 over 25, and probability of A given C is this probability A and C divided by probability of C, and that comes out to be 2 over 5 again. So it appears that this conditional probability, when you are told suddenly experiment was performed without replacement, does not change the probability, even though you know that when you perform this two-part experiment without replacement, that is, you take out a ball, throw it away, and then perform the second part of experiment on remaining balls, you are changing the nature of the experimental setup for the second run of the experiment. But the probability of getting a green ball in the second part of the experiment is same as if you had not thrown the ball you took in the first run of the experiment. And so is the case for getting a red ball on the second part of the experiment. Why is it so? It will be clear when we will discuss the concept of total probability in a few minutes. Let's look at another example of conditional probability. For the same case of two sacks with 3 green and 2 red balls, let's define event A to be that second ball was red, and event B to be that the first ball was green. If the experiment were performed using with replacement technique or as a joint experiment, then you know that the probability of second ball being red is equal to 2 over 5. But if the experiment was performed using without replacement methodology, then things will change. Then probability of second ball being red given that the first ball was green is half. It's not 2 over 5, it increases to a value of half. How is that? You can either think aloud and work this out, or you can manipulate the two-dimensional sample space with 25 entries to come up with that answer. Let's do this thinking aloud part first. You see, when you perform the first part of the experiment and get a green ball, and then you throw away the green ball, then in the sack there are 2 green balls and 2 red balls. And if you shake the sack and take out a ball, then probability of that ball being red is equal to 2 out of 4 or half. Now, if you want to manipulate the probabilities in the two-dimensional sample space, you have to be careful and find out probabilities of many events that are intersecting. But if you do that, you will find that the intersection of probability of second ball being red and first ball being green is just 6 entries. So it is 6 over 25. And when you condition it on the event that the first ball is green and divide it, you come up with half, and you can do it on that two-dimensional sample space. Now let's talk about the concept of total probability. In most complex experiments, an event occurs through many possible multiple paths. When I say complex experiment, I mean multi-part experiment. So if you are performing a multi-part experiment, then a particular event can occur through different sequences of events, where different sequences mean different outcomes in different parts of the experiment. In that case, if you want to find the probability of a given event, then it is sum of probabilities of all the paths leading to that event. This is sometimes also called the partitioning problem, where you have an event and you condition it on a collection of events, and that collection of events forms a partition of the sample space. What do you mean by partition? That is, this collection has members which are disjoint. No two members have any common area, and when you take union of all those members, you get the sample space. So you partition sample space into multiple sub-regions, and you take an event and you condition that event on this sample space which has been partitioned, and then you can see, as it is shown in this slide, that this leads to very interesting sequence of operations. If the partition is formed by a few sections of sample space called B1, B2, B3 up to Bn, then union of all these Bn's is equal to S, and no two Bi's and Bj's have any common element. If that's the case, then probability of A is same as probability of A intersection with S, the sample space, because when you intersection A with sample space, you get your A back. And then you break this sample space as union of B1, B2 and Bn, and then change the sequence of operation of intersection and union, and you get this as probability of union of a few events, where these events are A intersection with B1, A intersection with B2, A intersection with B3, etc., etc. And since these Bn's are disjoint, these new events where A has been intersected with these Bn's are also disjoint. Hence, using the axiom probability, we can add the probabilities of A intersection with Bn. Hence, as shown in slide, the last result is that probability of A is equal to sum of probabilities of A intersecting with different Bi's. And if you look at the formula for conditional probability, this probability of joint event A intersection Bn can be written as multiplication of conditional probability of A given Bn multiplied by the unconditional probability of Bn. So if you have a partition of sample space and you know unconditional probabilities of different parts of this partition, and then you take an event and take intersection of this event with different parts of the partition, then the probability of A, the unconditional probability, is sum of probabilities of these partitions multiplied by conditional probability of this event over these partition elements put together. Perhaps this will be clear if you look at the next slide, which takes again the example of two sacks of green and red balls. So we are going to partition this sample space S into B1 and B2, where B1 represents the event first ball being red, and B2 represents the event first ball being green. And this is referring to the first part of the experiment. So the whole sample space of the first part of the experiment has been divided into two parts, B1 and B2, and the first ball is red, B2 is the first ball is green. Now let's take an event A over this complex two-part experiment, and this event is that second ball is red. Now let's condition this event on the two elements of partition, B1 and B2. Hence, the probability of A, that is the second ball being red, is equal to summation of two things. First is, what is the probability of second ball being red given that the first ball was red? And you multiply that with the unconditional probability of first ball being red. Add to this the conditional probability of second ball being red given that the first ball is green, and multiply this with unconditional probability of first ball being green. If you put all the numbers together, you will find that this number comes out to be 2 by 5 again, which is equal to the probability of a ball being red, whether you are doing experiment with replacement or without replacement. This is not coincidence. If you work out the number, you will find that in this type of multi-part experiment where you have a sack with balls of two colors, then the probability of second ball being of a particular color is same if you perform the second part of the experiment with replacement or without replacement technique. Let's look at another example of total probability. And this example is that we talked about in the last lecture of TV game show, where you select a door and then you are given an option to switch. And then we are interested in finding the probability of you winning a prize. This is a problem of total probability when the sample space is just 4 doors, door 1, door 2, door 3, and door 4. And the partition of this sample space is in such a way that door 1, if it has a prize, is partitioned into one part and the other doors are partitioned into second part. Then probability of winning without switching comes out to be that you start with this partition and find the conditional probability of winning without switching with condition on this, plus probability of winning without switching condition on the other part of the partition. And similarly, probability of you winning with switching is equal to summation of two parts. First part is that you start your game by choosing the door with prize behind it and then you switch. And the second part of the partition is that you select in the first part of the game show a door which does not have prize. If you put all these numbers together, as I have done on this slide, you will see that probability of you winning by switching is equal to 3 by 8 and probability of you winning without switching is 1 by 4, which is less. Hence, it is to your advantage that in such a situation you should switch. By the way, if we have more than 4 doors, like 10 or 12 or 15 doors, then the difference between the probabilities of winning by switching and not switching becomes smaller. But in any case, the probability of winning with switching is always higher than probability of winning without switching. To summarize what we have done in this 5th lecture, we started with events and different ways to combine these events to make new events and talk about probabilities of these events. And the two ways that we combine these two events are through the idea of joint probability and conditional probability. And you can extend these ideas to find total probability of an event when that event occurs through multiple sequences of parts of the experiment. All these ideas were applied to few examples of discrete random spaces where the total sample space was a finite either 5, 25 or 4 outcomes. In coming lectures, we'll extend these ideas to other concepts of probability theory for discrete random spaces, and then we'll go to continuous sample spaces. Thank you.